everyone, once again I am Rosito Orquesta and welcome back to Pantas Malaya. Today we'll talk about two different things. The first one is the Big Bang and theory on the beginning of the universe and its alternative theories. Then the second one is we'll talk about the quantum mechanics or the quantum physics, the theories of quantum mechanics. So okay, so first thing and foremost, let's talk about the developments in contemporary physics, because the Big Bang theory and its alternative, as well as the quantum physics or quantum mechanics, belongs to the physics branch of science. It belongs to the contemporary physics. It is a revolutionized version of the classical physics. To understand what is the difference between classical physics and the development of contemporary physics. So the contemporary physics talks about the current development of science as an evolution of physics. Among these modern branches of physics are quantum physics, special relativity, and general relativity. So there are branches of science, and then there are branches of physics. So these are the three main branches of physics. Contemporary physics, we have the quantum physics, the special relativity, and then the general relativity. Quantum physics talks about the quantum world, while the special relativity talks about the relation between the space and time. If you can still remember Einstein, so special relativity is the biggest contribution of Einstein. Formula, the E equals mc squared. First thing is, let's talk about quantum mechanics. First, we'll talk about the quantum mechanics. So it is a fundamental theory of physics, theory in physics that provides a description of the physical properties of a nature that at the scale of atoms and subatomic particles. So in our previous years in elementary, in high school, I'll talk about atoms as the smallest particles in a matter, but there is this what we call subatomic particles. So these subatomic particles belongs to the quantum world. It is the main subject matter of quantum mechanics, the subatomic particles. So a fundamental feature of the theory is that it usually cannot predict with certainty what will happen, but only give probabilities. Mathematical probability is found by taking the square of the absolute value of a complex number known as a probability amplitude. So we'll talk much deeper about quantum mechanics on the next slides. Then the special relativity, so a scientific theory regarding the relationship between space and time, as I have said before a while ago, and Albert Einstein's original treatment. The theory is based on two postulates. So the first postulate is that the laws of physics are invariant, that is, identical in all inertial frames of reference, that is, frames of reference with no acceleration. And then the second postulate is the speed of light in vacuum is the same for all observers, regardless of the motion of the light or the light source or the observer. So these are the two postulates with regards to the special relativity of Albert Einstein. These are the theory on special relativity. So special relativity has a wide range of consequences that have been experimentally verified. So they include the relativity of simultaneity, length contraction, time dilation, the relativistic velocity addition formula, the relativistic Doppler effect, relativistic mass, a universal speed limit, mass energy equivalence, the speed of causality, and the Thomas precision. So these are the things, the range of consequences that you have to verify if we talk about special relativity. Also, special relativity was published by Einstein due to the incompatibility of Newtonian mechanics with Maxwell's equations of electromagnetism, and experimentally the Michelson-Morley null result and subsequent similar experiments so demonstrated that the historically hypothesized luminiferous ether did not exist. So special relativity talks that it has, for example, replaced the conventional notion of an absolute universal time with the notion of a time that is dependent on reference frame and spatial position. Rather than an invariant time interval between two events, there is an invariant space-time interval. So combined with other laws of physics, the two postulates of special relativity predict the equivalence of mass and energy. So as expressed in the mass energy equivalence formula of Einstein, which is the E equals mc squared, where c is the speed of light in a vacuum. So it also explains how the phenomena of electricity and magnetism are related. And then if we talk about general relativity, so the geometric theory of gravitational published by Albert Einstein on 1915 and is the current description of gravitation in modern physics. So general relativity generalizes special relativity and refines Newton's law of universal gravitation, so providing a unified description of gravity as a geometric property of space and time, or four-dimensional space and time. In particular, the curvature of space-time is directly related to the energy and momentum of whatever matter and radiation are present. So the relation is specified by Einstein field equations, a system of partial differential equations. So with this picture, so this is the comparison of the quantum physics and the classical physics. Other term is classical mechanics and quantum mechanics. So this means that the bigger the object is and the slower its speed, it belongs to the classical mechanics. But the smaller the size and then the faster it is, it belongs to the quantum mechanics. So that's the difference between classical and quantum physics. So classical physics is usually concerned with everyday conditions like speed are much lower than the speed of light, sizes are much greater than that of atoms, yet very small in astronomical terms. While modern physics, however, is concerned with high velocities, small distances, and very large energies. In relation to the developments in contemporary physics or modern physics, different theories about how the universe starts pop up in scientific community. The following are the known alternatives of the Big Bang cosmology theory. But to understand the Big Bang cosmology and its alternative theories, maybe we have to go back to the Big Bang cosmology itself. Let's talk about how Big Bang works, or how Big Bang has happened. Because Big Bang cosmology theories is not maybe it's not just me, maybe some other person or some other human that lives today thinks of the Big Bang cosmology or the Big Bang theory is just like a big explosion of unscattered things from different position in the universe. So, and just like that, it happens to create these heavenly bodies, these planets, the stars. So that's not how it is. It takes years and years of developments, the Big Bang. So back in the day, I thought that the Big Bang cosmology is about just like a big explosion, like when it happened, it automatically create the stars and other objects in the universe, like the planets. So it happened in a second or in a millisecond, and then just like that. But it never did was. Big Bang is a million of years and process, so it doesn't happen in just a millisecond, and then there you are. Humans live on Earth, and then no, that's not what it means. Big Bang is. So I was kind of like, um, that was my thought. Okay, so with that in mind, let me talk about how Big Bang happened with the recorded explanation of how the Big Bang works by notable scientists. But for the scientific community, this was and still a big question. So how was our universe created? How it happened? So how did it come to be the seemingly infinite place we know of today, and what we will become of it? So ages from now, and then these are the questions that have been puzzling philosophers and scholars since the beginning of time, and led to some pretty wild and interesting theories. But today, the consensus among scientists, astronomers, and cosmologists is that the universe, as we know, it was created in a massive explosion that not only created the majority of matter, but the physical laws that govern our ever-expanding cosmos. So, from the word itself, the Big Bang. So, it was created. The universe was created by a massive explosion, but the development of the planets and stars does not happen in a second, but in million years. So I have here a picture of a Big Bang theory. So at 10 to the power of negative 43 second, the Big Bang starts. Then there's the second phase is about 10 to the power of 34 seconds. Then the third one is the 10 to the power of 10 seconds. Then the 1 second, the 3 minutes, the 3,000 years, and then the 1,000 million years, and then the last phase is the 15,000 million years, or the current era of since the Big Bang happened. So the basics of the theory are fairly simple. In short, the Big Bang hypothesis states that all of the current and past matter in the universe came into existence at the same time. So roughly, it was 13.8 billion years ago. This time, all matter was compacted into a very small ball with infinite density and intense heat called a singularity. And suddenly, the singularity began expanding, and the universe, as we know, it began. So, literally, it does not happen with a big explosion, just like we imagine in movies that it scattered all the massive structures in the universe. So, but the singularity began expanding. It expands, and the universe, as we know, it began. Singularity term, also known as the Planck epoch or the Planck era. So this was the earliest known period of the universe. At this time, all matter was condensed on a single point of infinite density and extreme heat during this period. So it is believed that the quantum effects of gravity dominated physical interactions, and that no other physical forces were of equal strength to gravitation. So let me create let me draw the concept of Big Bang. So say for example, if this is your singularity. Okay, so this is now the singularity right here. Let us say that singularity, also known as the Planck epoch or the Planck era. So this was the earliest known period of the universe. Let's say that all matter was condensed on a single point of infinite density. So this is the single point. Okay, so this is your single point. This is your Planck epoch or the Planck or the singularity itself. So, and then it is believed that the quantum effects of gravity dominated physical interactions, and that no other physical forces were equal to the strength of gravitation. All matters are condensed on a single point of infinite density, so with extreme heat. And then this Planck period of time extends from 0 to approximately 10 to the power of 43 seconds. So if we are to picture that, it will be like this one. So 10 to the power of negative 43 seconds. Okay, so this is now your first period of Big Bang, the first phase of Big Bang. So it began to expand, it began to scatter at around 10 to the power of 43 seconds. So and is soon named because it can only be measured in Planck time. So due to the extreme heat and density of matter, the state of the universe was highly unstable. It thus began to expand and cool, leading to the manifestation of the fundamental forces of physics. So the Planck epoch, working backwards from the current state of the universe, scientists have theorized that it must have originated at a single point of infinite density and finite time that began to expand. So if you look at into our demonstration, our drawing, so from that black point, single point or the singularity, we created a rate expansion up to 10 to the power of 43 seconds. So that is the Planck epoch, the beginning of the universe. So it expand. Okay, and then after the initial expansion, the theory maintains that universe cooled sufficiently to allow the formation of subatomic particles and later simple atoms. The giant clouds of these primordial events later coalesced through gravity to form stars and galaxies. So that's how it happens. So those giant clouds are the origins of the stars and the galaxies. So the as well as the planets as a product or byproduct of the subatomic particles that later develop into simple atoms. So that was after the Planck epoch. So this all began roughly with 13.8 billion years ago and is thus considered to be the age of the universe. Through the testing of theoretical principles, experiments involving particle accelerators and high energy states, and astronomical studies that have observed the deep universe, scientists have constructed a timeline of events that began with the Big Bang and has led to the current state of cosmic evolution. So after the Planck epoch, the next scenario is inflation epoch. So with the creation of the first fundamental forces of the universe, the inflation epoch began, lasting from 10 to the power of negative 32 seconds and the Planck time. to an unknown point. So if we are going to draw the continue this drawing, okay, so let's expand more our drawing. So this is now the inflation epoch. So 10 to the power of negative 32, 10 to the power of negative 32 second. Okay, so most cosmological models suggest that the universe at this point was filled homogeneously with a high energy density, and that the incredibly high temperatures and pressure gave rise to rapid expansion and cooling. So because the singularity is condensed and heat, too much heat, it began to expand, it inflate, so from the Planck time to the inflation epoch, and then it begins to cool itself and forming, in the process it forms the universe. And so this began at 1037 seconds, 10 to the power of 37 seconds, where the phase of transition that occur calls for the separation of forces also lead to a period where the universe grew exponentially. It was also at this point in time that baryogenesis occurred, which refers to a hypothetical event where temperatures were so high that the random motions of particles occurred at relativistic speeds. So from negative 32 to negative 37. So let's expand more. This is our 10 to the power of 37 secant. So it is where so at this point in time that baryogenesis occurred, so it refers to the hypothetical event where temperatures were so high that the random motions of particles occurred at relativistic speeds. So it is at a time that the theory on space and time firstly manifested since the beginning of the expansion from singularity to the inflation epoch. And as the universe continued to decrease in density and temperature, the energy of each particle began to decrease, and phase transitions continued until the fundamental forces of physics and elementary particles changed into their present form. Since particle energies would have dropped to values that can be obtained by particle physics experiments, this period onward is subject to less speculations. So here the next phase is what we call the cooling epoch. Okay, so the first is the singularity, this one, and then it began to expand, what we call the Planck epoch. So this is the singularity, this is the Planck epoch, and then the inflation, this is the inflation epoch, and then the cooling. Okay, so singularity, the Planck, the inflation, and then the cooling. So for example, scientists believe that about 10 to 11 seconds after the Big Bang, particle energies drop considerably at about 10 to the power of 6 seconds. So quarks and gluons combine to form baryons, such as protons and neutrons, and a small excess of quarks over antiquarks lead to a small excess of baryons over antibaryons. Last of the Big Bang is the last phase of the Big Bang theory is the structure epoch. So this is now the structure epoch. Singularity, the Planck, expand more to inflation rate, then the cooling phase, and then the last one is structure epoch. So over the course of the several billion years that followed, the slightly denser regions of the almost uniformly distributed matter of the universe began to become gravitationally attracted to each other, they therefore grew even denser, forming gas clouds, stars, galaxies, and other astronomical structures that we regularly observe today. So during the structural epoch, this is the most recent actions that happened since the singularity. So in this epoch, it is where the stars and the planets or any other astronomical structures are formed, because they grew even denser, forming gas clouds and stars and galaxies. So if we go back to the picture I have presented a while ago, this Big Bang theory. So if you can see here, so this is your singularity, and then you have your Planck. So this is your Planck epoch. Here up to here, then it began to expand. So this is your singularity, this is your Planck epoch, this is your expansion epoch, and then after that expansion, the cooling phase. Okay, so maybe here, and then the last one is the structure. Okay, so these are your moments in a Big Bang theory. So you have your singularity point, then it began to expand because it cannot hold the heat of that singularity. So it is so much dense. All the matters inside that singularity began to expand at Planck epoch. Then the inflation epoch, it continued to expand. Then cooling phase. Then the last one is the structuring of the universe. So now we have these long-term predictions. So hypothesizing that the universe had a starting point naturally gives rise to the questions about a possible endpoint. So if the universe began as a tiny point of infinite density that started to expand, does that mean it will continue to expand indefinitely, or will it one day run out of expansive force and begin retreating inward? All matter crunches back into a tiny ball. Hence this idea. The universe was formed from a singularity. So this is the singularity. So the theory is that from this singularity it began to expand. Will there be a time that the expansive force will lose its force itself, and then instead of continuing to expand, it will create a big crunch, so it will shrink back to the singularity. Okay, so it will retract, expand, and then sink back to a singularity. Will there be a time that it will happen? So that's the long-term predictions. A prediction. But among these concepts, there are other alternative theories of Big Bang. So it's not just the Big Bang theory on how the universe started. So there are alternative theories hypothesizing that the universe had a starting point naturally give rise to questions about a possible end point. So if the universe began as a tiny point of infinite density that started to expand, does that mean it will continue to expand indefinitely, or will it one day run out of expansive force and begin retreating inward until all matter crunches back into a tiny ball? So among these alternative theories is the oscillating universe. So in this view, the mass density of the universe is sufficient to slow down and then reverse the expansion of the universe. This would lead to the Big Crunch, where the universe collapses back on itself. So after the Big Crunch, the universe would bounce and be reborn as another Big Bang, and this Big Bang would be followed by another Big Crunch, which would be repeat in an infinite cycle. So the oscillating universe theory is that the Big Bang itself will continue or will repeat its action in an infinite cycle. So it will expand, it will reverse the action. So it expands, it shrinks, and it expands again, then shrinks back to a singularity, then again expand. So that is the concept of the oscillating universe. So all life will end during the Big Crunch, okay, and then another form of life will be present on the next bounce of the Big Bang. So it will be an infinite cycle. That is the theory, or the oscillating universe theory. Now, but there are several things wrong with the oscillating universe. The first thing is that the best evidence today suggests that the density parameter is too small to halt the expansion of the universe. So as per calculations by the scientific world, it is suggested that it would never happen because the density parameter is too small to halt the expansion. So the density parameter could not stop the expansion. It will continue to expand at unprecedented length, okay, or space. Now the second one is, even if the universe were destined to contract someday, no known mechanism would cause it to bounce. So we would expect that once the universe imploded, it would remain in some sort of black hole state. Incidentally, if the Big Bang started in this sort of state, then this would be a problem for the single Big Bang model as well. So, okay. So the problem is the scientific world could not calculate that there is a much greater force that will hold the expansion rate of the Big Bang. And then the second one is, if it will make a crunch or it will implode, there is no existing formula or computations that would explain how would the next Big Bang would occur. So there is no known reason for it to happen. So if it implode, if the Big Bang implode, if all the matters implode into another singularity, maybe it will remain a singularity or a black hole state, okay, like a vacuum state. The third one is, there is no way that we can test this, so it is hardly a scientific concept. So it is not a scientific concept if it can't be tested. It will remain a concept. It will remain just a concept if we can test it. Because with science, if it can't be tested or if it can't be observed, it is no way a scientific concept. It is hardly a scientific concept. It will just remain a plain concept, an imaginative theory, the oscillating universe. Then the second alternative theory on the Big Bang is the infinite universe. So if the universe is infinite in size, then it has always been and always will be infinite in size. as the universe expands, it becomes larger and cooler, and its density decreases. So, what if the universe has been expanding forever? So, one possibility is that the physical laws that govern the universe change as the average temperature changes. So, this is the essence of the Grand Unified Theory, or GUT, that most physicists think that the fundamental forces that we observe today are different manifestations of a single force that has had its symmetry broken. Perhaps they think in much earlier times, when the universe was much hotter and denser, other laws of physics totally unknowable to us were in effect. If this were true, then what we call the Big Bang was just a transition from a much higher density and temperature state. The Big Bang would have been some sort of wall beyond which we cannot penetrate to earlier times with our physics. That's in the theory of infinite universe. Okay. So it talks about the infinite size, immeasurable size of the universe. So it is that as the universe expands, it becomes larger and cooler, and its denser decreases, or then the density decreases. So what if the universe has been expanding forever? So the physicists, or most physicists, think that the fundamental forces that we observe today are different manifestations of a single force that has had its symmetry broken. So they think that in much earlier times, when the universe was much hotter and denser, other laws of physics totally unknowable to us were in effect. So during the singularity, where all matters are denser and hotter, there is a physics in that current time that the physicists could not explain. So that's what the infinite universe suggests. So, but its symmetry is broken. So perhaps that's the reason why it began to expand, and it will continue to expand. Unlike the oscillating universe theory, that it will reach a maximum expansion and then implode back to a singularity. So the infinite universe talks about the continuous expansion without end. So because the symmetry of the unknown physics during the singularity, if this were true, then what we call the Big Bang was just a transition from a much higher density and temperature state. So the Big Bang would have been some sort of wall beyond which we cannot penetrate to earlier times with our physics. So the Big Bang is just a wall. So not a physical wall, but a concept that divides the physicists, the scientific community, on solving what was the physics was like on or during the singularity, before the expansion or the Big Bang happens. So basically, infinite universe theory is that the universe will continue to expand. Unlike the oscillating universe, it will not implode back to a singularity. It will continue to expand. The next one is the steady state. So this theory has a view that the universe is always expanding but maintaining a constant average density. So unlike the Big Bang theory, that the density is at a constant change during the expansion, steady state says that while expanding, it maintains the constant average density, matter being continuously created to form new stars and galaxies at the same rate that old ones become unobservable as a consequence of their increasing distance and velocity of recession. So because of the continuous expansion that happens, the previous universes that happened or been created were not observable by the current technology because of the distance. So the increasing distance and the velocity of recession. So a steady state universe has no beginning or end in time, and from any point within it, the view on a grand scale, or the average density and arrangement of galaxies is the same. Galaxies of all possible ages are intermingled, according to the Encyclopedia Britannica of 2021. So, if we are to draw the concept of the steady state, so all universes or all matters in the universe are already formed. So it contradicts to the concept of Big Bang theory, that it starts with a singularity and began to expand. The steady state is telling us that the objects in the universes are already existed. What happens is that it expands, and it continue to expand. That makes some other universes unobservable because of the increasing distance. So if you can imagine a rubber band, so imagine this: we have a rubber band. In the surface of the rubber band, you have your dots or points. If you relax your rubber band and create those points at a closer distance, what will happen is when you pull the rubber band from both sides, these dots will scatter. So the dots will stay the same, but the distance increases. So it will move away from each other. Okay, the dots. If you try to pull the rubber band on both sides, so basically that's what the steady state want to explain about the theory of how the universe expands or starts. It contradicts to the Big Bang theory that the universe has this singularity or the beginning, and it contradicts to the oscillating universe that one day, so somehow, the universe will stop expanding and it will implode and back into a singularity state. And then the next theory is about no boundary proposal, so made popular by James Hartle and the late Stephen Hawking. So we all know Stephen Hawking. So we'll discuss this in a bit, but first a brief review of a potential bound and unbound universe. So space can be bound or unbound. Being bound refers to space having an edge or boundary. So if we talk about bounds or boundary, so the space having an edge or boundary. In two-dimensional space, a tabletop is bound because it has a definite boundary. It has a definite size. The edge of the tabletop, and on the other hand, a mathematical plane, would be unbound because it extends indefinitely in all directions. So if we talk about the physical tabletop, it has an end, so therefore it is bound. It has width and length, so that is bound. But if we talk about on a mathematical plane, it will be unbound because space continues to extend and expands indefinitely in all directions, so long as you can imagine. Then no boundary proposal, according to Hawking and Hartle, the no boundary proposal according to the general relativity. Space may have some overall curvature, so it is possible that space may curve back upon itself so that it has no boundary, but it is finite in size. So the space has finite size, but it has no boundary. So if we consider a two-dimensional example, a flat two-dimensional object such as a paper or a piece of paper is usually finite in size. So you can measure the the width and the length of a two-dimensional piece of paper. So it has a boundary. On the other hand, the surface of the earth is two-dimensional, so, but it is curved back onto itself. Therefore, the surface of the earth has no boundary or edge, but it is finite in size. So with this example, so if you consider the globe, if you consider the earth, it is a rounded object in the universe like this one. Okay, so it has a finite size because we can measure the actual size of the earth, but the thing is, it has no boundary, because if you travel from one place to and continue in a straight line, you will be back to your point of origin because of the curvature. Theorized by Hartle and Stephen Hawking that the universe works the same. It is finite in size, but has no boundary or edge, because the space curved back onto itself, just like the surface of the earth. So if the universe is closed back on itself, and if you have traveled in a straight line, you would eventually return to your starting point, such as the universe would be finite in size and unbound, and thus we could avoid both an infinite universe and a bound universe. So the Hartle-Hawking new boundary proposal is a different twist on Big Bang cosmology. So in general relativity, space and time are treated similarly in a four-dimensional space, but quantum mechanics suggests that time loses meaning in an interval shorter than 10 to the power of negative 43 seconds, so becoming like the other three spatial dimensions. Consequently, time has no meaning in the first 10 to the power of negative 43 seconds after the Big Bang universe, leaving the Big Bang unbound in time. This leaves the origin of the Big Bang meaningless. So there is a time of the Big Bang that has no meaning at all. So another theory is the antimatter universe. So this was proposed by Latham Boyle and Neil Turok. This is an alternative to the no boundary proposal. So it postulates that our universe came into existence at the Big Bang period with a sort of mirror image universe. So unlike our universe, the mirror image universe is dominated by antimatter and expands backward onto time. So if we are to draw the concept of the antimatter theory, it will be like this. So on the point of origin, or in the center of where the Big Bang starts, so there will be an imaginary line, where on the right side is where the expansion of the singularity happens, or the Big Bang happens, the Planck epoch, and then the expansion, the cooling state, and the structure. And then at the same time, on the other side of that imaginary line from the singularity, we have this another expanding antimatter, which is equivalent to the length of, or to the expanding rate of our universes. So but these are purely antimatter. So it's like a separation of matter and antimatter. So the Big Bang happens because it separates matters and antimatter. So we have this imaginary mirror that divides the matter and antimatter. So this side here is matter. So universes forms in this side, while on the other side is the antimatter. So basically the concept is Big Bang is trying to separate matter from its antimatter. So that's what the antimatter universe theory is. So there is a mirror-like or image universe on the other side. So if the Big Bang is created in matter on the positive side, so we're going forward in time, so positive forward in time. The antimatter is going backwards, negative, backwards in time. And then another theory is the string gas cosmology. This was proposed by Cameron Bavafa and Robert Brandenburger. The most popular theory of elementary particles today is string theory, which posits that particles are vibrations like vibrations on a string, hence the name. So a variation on strings theory is superstring theory, a combination of string theory with gravity via a concept called supersymmetry. So the string gas cosmology suggests that a dense gas of superstring came first, from which the universe sprang. So if we are going to draw the string gas cosmology, this is what it looks like, the string gas cosmology. So according to Vafa and Brandenburger, universes is a string gas cosmology. A dense gas of superstring came first. So there is this string-like gas cosmology. Okay, maybe I will do it with a circle string, superstring. Okay, so I have two strings here. One is that connected to the other end, that it loops, and a broken string. Okay, so what happens is that in a gas string cosmology, all universes are produced within the vibrations of these strings. So if you can imagine the string of a guitar, when you strum a guitar, it will vibrate. So with that vibration comes the universes. So the universes sprang within that vibrations, and then with that vibrations it created the gravitational force. So if this is your your superstring, so this is your superstring, and it vibrates. From that vibration it creates the universes, and it produces the gravitational force. So these red structures are the universes, and this black line is the superstring of gas. So and then let's try to imagine that superstring is in a shape of a donut. So like this circle I have drawn. So and then it continues to vibrate. So this is your string, your superstring. This string wraps around on a donut shape superstring, and from that universes are formed. And because of its structure, the donut shape superstring, it creates forces that represents the gravitational force. So that would be your string gas cosmology. One thing that is wrong about string gas cosmology is that if there is a superstring as thought by Vafa and Brandon Berger, there will be these small strings. So the universes will be composed of not just a superstring but some other strings. So there might be small scale strings that will be flying around and should be observable. These strings will might at a certain point in time entangle to each other. And when it happens, supposedly there would be a catastrophe. So the science community thought that if there is these strings of gases, and it should be observable. And if you can observe the string gas, say for example, if that string gas is run across a star. So let's say for example, if this is your star, okay, this is your star, and then a single strand of string gas will pass through these stars. This star might be turned into half. It will be sliced, and if it is observable, you would then see two identical stars. So instead of half, you would see two equal stars, because with the string crossing the star, it will produce a curved image, right and to the left side of that string gas, forming two mirrored image of the same star. But this phenomenon is not being yet observed, so therefore the scientific community never accepted the superstring or the string gas cosmology. Next theory is about the change of phase. This was formulated by Daniel Oretti and Lorenzo Sendoni, Edward Bolson Ewing, and Stephen Galen. So one speculative view of physics is that space and time, or space-time, consists of tiny particle-like bits, just as atoms or molecules organize themselves into three phases of matter, like the solid, liquid, and gas. Perhaps the particles of space-time condense to produce the universe. So, with increasing temperature, we see a succession of phase transition for water in which its properties change dramatically. So the solid phase is the ice, then it melts to the liquid phase, which is the water, and then eventually boils to the gaseous phase, or the steam. So you should notice that steam is more symmetric than the water, and then that the water is more symmetric than of the ice. So also it is with matter in our universe. So it begins in a unified or symmetric phase. So as we will explain below, that then passes through a succession of phase transitions until at lower temperatures. So we finally obtain the matter particles with which physicists are familiar today. So the electrons, the protons, neutrons, photons, and etc. So first order phase transitions proceed by bubble nucleation. So a bubble of a new phase, then a true vacuum forms and then expands until the old phase, or the false vacuum, disappears. A useful analog is the boiling water, in which bubbles of steam form and expand as they rise to the surface. So during the first order phase transition, the matter fields get trapped in the false vacuum state, from which they can only escape by nucleating bubbles of the new phase, that is the true vacuum. So if we are to draw the change of phase, universe, the matter of universe is changing its phase. So let's say for example there are a true nucleating bubbles. So say for example these are your bubbles. So you have these tiny and big bubbles. Okay, so during the first order phase transition, the matter fields get trapped in a false vacuum. So say for example this is your false vacuum. Okay, so and then the matter is trapped inside this false vacuum, which they can only escape by nucleating bubbles of the new phase, that is the true vacuum state. So it must create a true vacuum state. So let's draw a true vacuum state here. So this is your true vacuum state. So what happens now is the matter that is trapped in a false vacuum will transcend to the true vacuum by nucleating, and this false vacuum will begin, okay, so forming a new bubble or a new vacuum. So this will form a new vacuum, a new true vacuum, a new state. So that's what happens to the universe as explained by Daniel, Lorenzo, and Ewing, as well as the Stephen Galen. Said that the atoms or molecules organize themselves into three phases of matter: the solid, the liquid, and gas, and then perhaps the particles of space-time condense to produce the universe. So from gaseous state, it condenses and then forming the universes. And so it is with matter in our universe. It begins in a unified or symmetric phase. So as we'll explain below, so the one I'm illustrating in a drawing, and then passes through a succession of phase transitions until at lower temperatures we finally obtain the matter particles with which physicists are familiar today: the electrons, protons, neutrons, and the photons. So from the solid state, so the universe or the singularity on the Big Bang theory is the solid state of that phase according to the change of phase. And then so let's go back to the singularity. So this your singularity in the Big Bang theory is the solid state of solid state of the change of phase theory. And then when it began to expand into the Planck epoch, the inflation, the calling, and the structure, those states are the changes of phase according to the change of phase theory, where the matter from the singularity passes through a succession of phase transitions until at a lower temperature. So we know that during the singularity, a singularity has a heat value that we can't imagine. It is a great heat value, and with that it began to expand until to the cooling phase, until it cools down. So that's what the change of phase theory trying to explain, that electrons, protons, neutrons, photons, and other familiar matter particles to the physicists today as produced by that change of phase during the Big Bang theory. It's still a Big Bang, but the alternative explanation of the Big Bang phases. So instead of the Planck epoch and up to the structuring epoch, it explains in a change of matter from solid to liquid and then to gas phase. So that is the change of phase. And then the next one is the next theory, alternative theory, is the bouncing cosmology. So the Big Bounce is a hypothesized cosmological model for the origin of the known universe. So it was originally suggested as a phase of the cyclic model or oscillatory universe interpretation of the Big Bang, where the first cosmological event was the result of the collapse of the previous universe. However, the Big Bounce states that the universe has been subjected to a state of expansion and compression one after another recurrently. So bouncing each time it contracts to a certain volume, and some suggest that the universe only bounced once. So in this model, the cosmos had been shrinking before the bounce, since the innumerable pass, and it will expand for the rest of the time. This is different, almost the same but different from the oscillating universe theory. The bouncing cosmology, unlike the oscillating universe, because oscillating universe theory is that it begins to expand and then implode and then explode again and then implode again in a cycle. But the bouncing cosmology, we don't begin with expanding, we begin with imploding. So if this is the singular, we are becoming into one singularity, and from that singularity we will bounce back. But after bouncing back, it will not shrink again. So in this model, the cosmos had been shrinking before the bounce since the innumerable pass, and it will expand for the rest of the time. So after imploding, after this implode, it will explode for the rest of the time. So that's the difference between the bouncing cosmology and the oscillating universe theory. The oscillating universe theory is cyclic. It goes in a cycle. The universe will expand and explode and then implode and then explode again in a cycle. But with the bouncing cosmology, it is right now imploding into a singularity, and then later on it will explode and never implode again. It will continue to expand to the rest of the time. That is the bouncing cosmology theory. Then another one is eternal inflation. So following the Big Bang, the universe expanded rapidly during a short period called inflation. The eternal inflation theory, on the other hand, presupposes that inflation never stopped but continued to happen for an infinite time span. So out there somewhere, even today, new universes are being created in an immense complex called the multiverses, or the multiverse. What is more, those numerous universes could have quite different physical laws from the ones we know. That's the eternal inflation. So from the theory of Big Bang, so we already know about the singularity, that it expand into the Planck epoch and then the inflation epoch. So this inflation epoch never stops in eternal inflation. On the theory of the Big Bang, the inflation has stopped because after the inflation begins the cooling state. So singularity, Planck epoch, the inflation. After that inflation, objects in the universes began to cool down, and after it cools down, it forms the structures of the universe. Uh, the planets we know today, the stars, and other cosmological uh, objects. So it stops here. The inflation stops this specific span of time during the Big Bang. But with the eternal inflation, the theory is that from that singularity, then expand to the Planck epoch. After that Planck epoch, it turns to the next phase, which is the inflation, and then that inflation didn't stop. So that inflation didn't stop, it continues to expand and continued to create universes. And then during that expansion, inflation, during that inflation, continuous inflation, the cooling state as well as the structuring state where it forms the matters, structuring state and the cooling state as continue to happen. So after the Planck epoch or the Planck period comes the inflation, and then that inflation continues to happen as well as today, and then within that inflation the cooling state and structuring is continuing to happen. It continues to structure or creating new universes, the multiverses, and it continues to cool down matters. Okay, so that's the difference between the eternal inflation and the Big Bang theory. And then comes the black hole theory. So there is another theory about a black hole. So the black hole theory says that our universe came from a black hole of another universe. Therefore, we are living outside its horizon, event horizon. In an alternate version of the theory, the observable universe is the inside of the black hole subsiding as one of the potential many within a larger parent universe or universes. So in this respect, we can claim that a new universe lies behind every black hole, given that we cannot pass the event horizon of a black hole. So there is no way to clearly prove or disprove this theory, because it is not because it can't be tested, or it can't be clearly observed. So the black hole theory is something like this. So maybe you have already know about black holes. So a black hole is a rip, or a somehow it's like a hole in time and space in the universe. So it's like a sink. Okay, if you imagine when you are trying to drain your washing machine, or when you are washing your dishes, your plates, and then you open you gather the water and then open the sink, it will form a circular pattern, and the water will form a circular pattern, and is shrinking to the middle. So that's how the black hole somehow, if you try to imagine a black hole, that would be the imaginative image of a black hole. Okay, so and then on the center of it there is somewhat a hole, where matters might pass through. So with the black hole theory, it is said that our universe came from a black hole of another universe. So this is a fine line here. Let me draw that fine line. This is universe 1. And then from that universe comes our universe. So this is our universe. So it passed through that black hole, making our current universes. Our current universe. So if you look at it, this is very similar to the antimatter universe, where our universe, which is composed of matter, is being separated or being separated from the antimatter universe. Okay. So in this theory, the black hole is that in an alternate version of the theory, the observable universe is the inside of a black hole, subsiding as one of the potential many within a larger parent universe or a multiverse. So these universes here are also produced by a black hole. So as well as our universe, the other observable universe are produced by a black hole. So we pass through the black hole. So that might happen that if a black hole will somehow sink our universe, it will produce another universe. And then after the black hole theory, there is these wild theories that life or the universe is just merely a simulation. Okay. So some insinuations found in string theory and quantum gravity persuasively suggest the universe is not at all as it seems. It is possible that the entire universe is just a flat hologram projected onto a spherical surface. Others suggest it could be an entirely digital simulation running in an enormous computer. So all life, all universes we can observe, all the bodies, cosmological bodies we can observe are just merely a simulation. So the simulation hypothesis or simulation theory is a proposal regarding the nature of existence. The proposals that all current existence, including the Earth and the rest of the universe, could in fact be an artificial simulation, such as a computer simulation. Some versions rely on the development of a simulated reality, so a proposed technology that would be able to convince its inhabitants that the simulation was real. The simulation hypothesis bears a close resemblance to various other skeptical scenarios from throughout the history of philosophy. So the hypothesis was popularized in its current form by Nick Bostrom. And I know that the CEO of the Tesla, which is the current CEO of the Tesla, has talked about that the life is just merely a simulation. He firmly, or maybe not firmly, but in a greater percentage, maybe 80% or 90%, believe that life is just a simulation, that we just live in a kind of supercomputer. So according to the CEO of the Tesla company, it's true, maybe, because like this point in 2003, philosopher Nick Bostrom proposed a trilemma that he called the simulation argument. So despite the name Bostrom's simulation argument does not directly argue that we live in a simulation. Instead, Bostrom trilemma argues that one of three unlikely seemingly propositions is almost certainly true. So the propositions are that the fraction of human level civilizations that reach a post-human stage, that is one capable of running high fidelity ancestor simulations as very close to zero, or the fraction of post-human civilizations that are interested in running simulations of their evolutionary history or variations therefore is very close to zero, or the fraction of all people with our kind of experiences that are living in a simulation is very close to 1. If you imagine that the current technology creates, we can already create simulations, okay? We can already create holograms, and then the AI simulations on a computer, in a game. You can even create this that mimics the reality, virtual reality and the augmented reality, where the virtual reality is that you play simulated space in a computer. You can even use a device that looks like you are inside that simulation. And then the other one is the augmented reality, where simulated objects are visible on or being placed or being put above the real scenario. If you have played the Pokemon Go, it is an example of an augmented reality. So with that in mind, the augmented reality, the virtual reality, the simulations, the AI, and even this the hologram technology. So you might think that the maybe somehow the life is just a simulation. And if you think if we got something from the Bible, a concept from the Bible, God has created the human according to its image, and because of that, God has created the human according to His image. Now, the humans or us are creating simulations, or creating holograms, creating virtual reality or augmented reality based on our actual images also. So we are mimicking the one that creates us. The action of the one we call God, we are trying to make the same. We are trying to mimic the action. We are trying to create a human-like. We even created a robot, right? The AI technology. So maybe somehow this has a point. Maybe the CEO of the Tesla has a point in believing, or 80% maybe believing that we live in a simulation. So it was according to Elon Musk. So there are other alternative theories proposed. So there are proposals based on observational skepticism. I didn't include the discussions on these proposals because it is really not a somehow scientific in its sense. So since the theories must be based on a scientific explanations, somehow at least percents of it are based on the so I didn't include these proposals based on observational skepticism. So the tired light, the redshift periodicity, intrinsic redshifts, plasma cosmology. So anyway, you can find these proposals on wikipedia.org. And then there are other alternatives and extensions to lambda CDM theory, which is the anisotropic universe, the exotic dark matter, the exotic dark energy. Just a little hint on the tired light observational skepticism theory. It is that it really does not talk about how the universe were formed, but it talks about why we cannot observe other universes
It is because tired light explained that uh, as the distance increases, the the light produced by the heat or the matter of the universe uh, becomes unobservable by the observer, where the current observer is. So like us and the earth, we cannot observe other um, objects because of the distance, and because of that distance and the Calling state. If you can still remember the Calling state of the Big Bang theory, so it produces the tired light. And then on the alternatives and extensions of lambda CDM, the exotic dark matter and dark energy, um, the main concept of this is that uh, we are, or the Milky Way or our universe is placed on a much on a place in the universe. Our galaxy is placed in part of the universe where there are lesser matter or lesser objects. That is why there are more dark matter or there are more dark energy. Dark energy is like a water. Explain like it's a water flow. So therefore, if you observe at night, you look up in the sky, there are more darker spots than the stars, right? So that's how the main explanation of this extensions of lambda CDM alternative theory. And then there are these alternatives to general relativity, the Machian universe, the MOND, the FR gravity, which are not really talking about the start of the universe, but the state of how universe is being observed. I didn't include this in my uh, presentation because it's somehow uh, so far from the main concept of alternative theories of the Big Bang. Okay, and then the second topics we have today is understanding the quantum theory. So the quantum theory talks about the quantum physics or the quantum mechanics. So if you try this or try to picture out that quantum world is another world that coexists with the current world we know, like you see matter, you see these things, these objects, but try to imagine the composition of that object, the composition of that matter, the composition of you as a human. So quantum physics talks about that composition. So let's try to understand quantum theory. So the first is, we'll talk about the quantum fluctuation theory by Edward Tyron. Stated that I offer the modest proposal that our universe is simply one of those things which happen from time to time. So Alan Guth has echoed this sentiment with the observation that the whole universe may be a free lunch. Indeed, Guth's inflationary model depends upon a quantum fluctuation as the origin of the Big Bang. So the origin of the Big Bang is a quantum fluctuation according to Guth. The singularity could not hold anymore the heat or the density of the matter, so it exploded. It began to explode into the epoch or the Planck epoch up to the last state, which is the structuring of the universes. Then quantum fluctuation theory of the origin of the universe has been expanded upon to allow for many other universes. In this view, the universe did not arise as a quantum fluctuation or ex nihilo, but instead arose as a quantum fluctuation in some other universe. So a small quantum fluctuation in that universe immediately divorces itself from that universe to become ours. So presumably, the universe also arose from a quantum fluctuation in a previous universe. Perhaps our universe is frequently giving birth to new universes in similar fashion. So if we are to demonstrate that concept, it will be like this. So the quantum fluctuation they are talking about is that this universe 1, so this is universe 1, there's a small fluctuation here that created a universe 2, and in the same manner there is a fluctuation in this universe 2 that will create a universe 3. So that is the concept of quantum fluctuation theory. Just a free lunch. And then let's talk about, since this is a quantum mechanics, quantum physics, quantum theory, we'll talk about particles. So known for his law of universal gravitation, English physicist Sir Isaac Newton, born in 1643 and died on 1727, realized that light had frequency-like properties, and when he used a prism to split sunlight into its component colors, nevertheless, he thought that light was a particle because the periphery of the shadow it created was extremely sharp and clear. So, the English physicist Sir Isaac Newton believes that because of his experiment, he believes that light was a particle. Okay, so lights are composed of particles. And then another physicist, Francesco Maria Grimaldi, so the wave theory, which maintains that light is a wave, was proposed around the same time as Newton's theory. So in 1665, an Italian physicist, Francesco Maria Grimaldi, which born on 1618 and died on 1663, discovered that the phenomenon of light diffraction and pointed out that it resembles the behavior of waves. So, contradicting to the theory of Newton, Grimaldi states that instead of particles, light is a wave, a form of wave. Then in 1678, a Dutch physicist, Christian Huygens, from Netherlands, established the wave theory of light and announced that Huygens principles. So we all from that point in time, we believe that light travels in a wave form because of the announced theory of light by Huygens during his times in around 1629 to 1695. But that concept is not the original of Huygens, but it comes from Francesco Maria Grimaldi, which is an Italian physicist. Okay, and then the theory of light being a particle completely vanished until the end of the 19th century when Albert Einstein revived it. So Albert Einstein revived the theory that the light is a particle. Now that the dual nature of light as both a particle and a wave has been proved, its essential theory was further evolved from electromagnetics into quantum mechanics, because Einstein believed that light is a particle or a photon, and the flow of photons is a wave. The main point of Einstein's light quantum theory is that light's energy is related to its oscillation frequency. He maintained that photons have energy equal to the Planck's constant times oscillation frequency. And this photon energy is the height of the oscillation frequency, while the intensity of light is a quantity of photons. The various properties of light, which is a type of electromagnetic wave, are due to the behavior of extremely small particles called photons that are invisible to the naked eye. So imagine, let's try to draw the concept of this known physicist from Sir Isaac Newton to Maria Grimaldi, Francisco Maria Grimaldi, and then to the Huygens, Christian Huygens, and then up to Albert Einstein. So the first theory is that lights are particles. So it may resembles like this dots. So they are particles. The lights are particles, like this one. And then Grimaldi and Huygens, this is from Newton, okay? And then Grimaldi and Huygens say that instead of particles, the light is a wave. But then Albert Einstein combined these two theories. According to Einstein, Newton was right that light really are particles or the photons. But these photons behaves or acts or moves like waves. So the motion of how these photons travel in space are so much like of that wave. So this is how Albert Einstein combined the theory from Newton that light are particles, and the theory of Huygens and Grimaldi that light is a wave. So by combining these two, so in a quantum physics or in quantum mechanics, there is what we call the quantum realm in our world. In our world, what we see are matters or atoms like this one. So we see the object, but what we cannot see is the quantum realm that is in a form of wave. So this one. So this circle here is really a wave. So this may be called particles or the atoms or the photons or whatever the particles this one is, but that really is in a form of wave. It behaves like a wave in the quantum realm. Now in quantum physics, we will try to measure this wave. We'll try to measure this wave instead of measuring this particle, this round particle here. We will measure this wave instead. But there is a measurement barrier because we cannot be precise, because all we can do when we compute the quantum realm is probable or probability. It's all about probabilistic. Okay. So to make it more interesting, let's view and a video.
Quantum physics has a mystique of being complicated and hard to understand. In fact, Richard Feynman, who won the Nobel Prize for his work on quantum electrodynamics, said, "If you think you understand quantum physics, you don't understand quantum physics." Which is kind of disheartening for us, because if he didn't understand it, what chance do the rest of us have? Fortunately, this quote is a little misleading. We do in fact understand quantum physics really well. In fact, it's arguably the most successful scientific theory out there, and has let us invent technologies like computers, digital cameras, LED screens, lasers, nuclear power plants. And you don't really want to build a nuclear power plant if you don't really understand how it works. So quantum physics is the part of physics that describes the very smallest things in our universe. Molecules, atoms, subatomic particles, things like that. And things down there don't quite work the same way that we used to up here. This is fascinating because you and everything around you is made from quantum physics. And so this is really how the whole universe is actually working. I've drawn these protons, neutrons and electrons as particles, but in quantum mechanics we really describe everything as waves. By the way, I'm using quantum physics and quantum mechanics interchangeably, they're the same thing. So instead of an electron looking like this, it should look something like this. This is called a wave function. But this wave function isn't a real physical wave like a wave on water or a sound wave. A quantum wave is an abstract mathematical description. To get the real world properties like position or momentum of an electron, we have to do mathematical operations on this wave function. So for the position, we take the amplitude and square it, which for this wave would look something like this. This gives us a thing called a probability distribution, which tells us that you're more likely to find the electron here than here. And when we actually measure where the electron is, an electron particle pops up somewhere within this area. So with quantum physics, we don't know anything with infinite detail. We can only predict probabilities that things will happen. And it looks like this is a fundamental feature of the universe, which was quite a departure from the clockwork deterministic universe in classical physics, the kind of thing Newton derived. This wave function model predicts what subatomic particles will do incredibly well, but weirdly we've got no idea if this wave function is literally real or not. No one's ever seen a quantum wave, because whenever we measure an electron, all we ever see is a point-like electron particle. So there's like this hidden quantum realm where the waves exist, and then the world we can see, which is where all the waves have turned into particles. And the barrier between these is a measurement. We say that a measurement collapses the wave function, but we don't actually have any physics to describe how the wave collapses. This is a gap in our knowledge that we've dubbed the measurement problem, and this is one of the things that Feynman was referring to with his quote. Another confusing thing is how exactly to picture an electron. It seems to be a wave until you measure it, and then it's a particle. So what actually is it? This is known as particle-wave duality, and here's an example of it in action, the famous double-slit experiment. Imagine spraying a paintball gun at a wall with two openings in it. You'd expect to see two columns of paint go through and hit the wall behind. But if you shrink this all down to the size of electrons, you see something quite different. You can fire one electron at a time at the slits, and they appear on the back wall. But as they build up over time, you get a whole pattern of stripes instead of just two bands. This pattern of stripes called an interference pattern, something you only see with waves. The idea is that it's the electron wave that goes through both slits at the same time, and then the waves from each slit overlap with each other, and where the waves add together you've got a high probability of the electron popping up at the wall, but where the waves cancel out the probability is very low. So actually on the back wall the highest probability of finding the electron is in the middle of the slits, and then it goes down and then up again and down and up again, and this is the interference pattern. So when you fire one electron after another, they follow this probability distribution, and this interference pattern starts building up, and that's exactly what we see in experiments. So this shows that electrons behave like waves in this experiment. The question is, what actually happens to this spread out electron wave when you do a measurement? It seems like it goes from this spread out wave to this localized particle. But like I said, there's nothing in quantum mechanics that tells us how the wave function collapses. And this is not only true for electrons, but everything in the universe. So this double slit experiment has huge consequences for our model of the universe. and it was very surprising the first time it was done. Physicists are still grappling with this question today and have come up with many interpretations of quantum mechanics to try and explain these results, and explain how reality actually works. Okay, let's go back to the wave function. We can now use this picture to explain other features of quantum physics that you may have heard about. So this is just one possible wave function for an electron, but there's many others, like this one for instance. This says that the electron has a probability of being over here and a probability of being over here, and very little probability of being in the middle. This is perfectly allowable in quantum physics, and this is where the phrase "things can be in two places at once" comes from. This is known as superposition, which comes from the fact that this wave can be made by adding, or superimposing, these two waves. The word superposition just means the adding together of waves, and we already saw this in the double slit experiment. And it's not really a very special phenomenon. You can even see superposition by dropping two pebbles into a pond where the ripples overlap. Now for entanglement. Let's say two electron waves meet. Their waves interfere with each other and become mixed up. This means that mathematically we now have one wave function that describes everything about both electrons, and they're inextricably linked, even if they move far away from each other. A measurement on one of the particles, like measuring if it's spin up or down, is now correlated with a measurement on the other, even if they move billions of miles away. Einstein was very uncomfortable with this idea because if you measure one of the particles here, you instantaneously know what the other will be, even if it's billions of miles away. And that's got a sort of whiff of faster than light communication, which is not allowed by the theory of relativity. But it turns out you can't actually use this to communicate information because the measurements give you random results. But the fact that they are correlated means that somehow there is a link that stretches over that distance. This is called non-locality. Quantum tunneling. Quantum tunneling is where particles have a probability of moving through barriers, essentially allowing things like electrons to pass through walls. When a wave function meets a barrier, it decays exponentially inside the barrier. But if the barrier is narrow enough, the wave function will still exist on the other side, meaning that there's a probability of the particle being found there when a measurement is made. In fact, the only reason you're alive is because of quantum tunneling in the sun, which makes the sun shine. Protons normally repel each other, but they've got a small probability of quantum tunneling into each other, which is what turns hydrogen into helium and releases fusion energy. All life exists on Earth because of energy from the sun, except for life around hydrothermal vents. Now onto the Heisenberg uncertainty principle. I said at the beginning that this wave function contains all of the information like position and momentum of the electron. We just have to do some maths on it. The position is given by the amplitude or height of the wave, and the momentum is given by the wavelength of the wave. But for this specific wave, the position gives us a probability distribution, so we don't know exactly where the electron is. Also, there's an uncertainty in the momentum because this wave is made of many different wavelengths. But we can reduce that uncertainty. Let's have a wave that only has one wavelength, so a sine wave. Now we know the momentum exactly because the wavelength has a single value. But look at the position. There's an equal probability of the electron being found anywhere in the universe. Okay, let's do the opposite. Let's make a wave that has only one position. Now we know exactly where the electron is, but what's the wavelength of this wave? Now the wavelength is very uncertain. Basically, only a sine wave gives you a precise momentum. And any wave that isn't a perfect sine wave, you have to build out of multiple different sine waves. In each of those multiple different sine waves has got a different wavelength, and hence you have a range of the possible different values of momentum for the particle. This is Heisenberg's uncertainty principle. You can only know certain things precisely, but not everything. Either you've got a definite value of momentum and don't know anything about position, or you know the position very well, but don't know anything about the momentum. Or you're in some intermediate state. And this isn't a limit of our measuring apparatus, this is a fundamental property of the universe. And finally, where does the name quantum come from? Well, a quanta is a packet of something, like a chunk of something. And one of the first quantum effects people saw were atomic spectra, which is where atoms give off light with specific discrete energies. It works like this. Imagine a string that's tied at both ends, like a guitar string. If you pluck it, only certain waves can exist because the ends are tied down. In this situation, we say that the wavelengths are quantized to certain values. The same thing happens if you tie the ends of the string together, because the waves have to match up. They can only vibrate in certain restricted ways. And this is what's happening to an electron in an atom. The electron wave is constrained by the atom and quantized to certain wavelengths. Short wavelengths have got a high energy, and long wavelengths have a lower energy. This is why the light emitted by an atom looks like a barcode, because each bar of light corresponds to an electron jumping from a wave with a high energy to one with a lower energy, and at the same time emitting a quantized photon of light when it does this. So the light from an atom is quantized to discrete packets of energy. Okay, so that's all the basics of quantum physics. Here are some technical notes which aren't essential to know, but pause the screen now if you're interested in a little bit more mathematical detail. So to round up, in quantum physics objects are described with wave functions, but when we measure them, what we see are particles. So this leads to particle-wave duality and also the measurement problem. And the consequence of these wave functions are the quantum phenomena of superposition, entanglement, quantum tunneling, the Heisenberg uncertainty principle, and energy quantization. So if you understand these things, you've got a good basic understanding of quantum physics. Despite its reputation, I think that quantum mechanics isn't too difficult for most people to get the basics of what's going on. In the past I've relied on analogies to try and explain it, but here I've just described what's actually going on, which I think might be more helpful. But if you've got more questions, I'll be on the comments below, so ask away. For me, the weird thing about quantum physics is that on the one hand it's incredibly accurate and predictive, but also it's got giant holes in it, like the measurement problem, which we just don't understand. So we can wonder, will we ever actually understand quantum physics, or is it just too abstract for our human brains to comprehend? Well, I hope this video has helped you understand a little bit more about how quantum physics works. And thanks to the sponsor of this video, Brilliant.org, who have just launched.
Okay, so that video must be an additional explanation on the quantum physics. It is very concise and informative video about understanding the quantum mechanics. So that the quantum mechanics is a composition of a quanta or a packet. So in an atomic spectrum, there are these packets, as you can see in this, or if you can see this representation of atomic spectrum, there are these packets here below. These are what quanta means, or a packet. So basically, quantum physics theory is based on these three truths. The first is quantized properties. So certain properties such as position, speed, and color can sometimes only occur in specific state amounts, much like a dial that clicks from number to number. This challenge a fundamental assumption of classical mechanics, which says that such properties should exist on a smooth, continuous spectrum. To describe the idea that some properties click like a dial with specific settings, scientists coined the word quantize. So, in theory, or in the classical mechanics or classical physics, it is the assumption is that properties should exist on a smooth, continuous spectrum. That just like what we have presented a while ago. This is the continuous spectrum, and then to describe the idea that some properties click like a dial with specific settings, scientists coined the word quantize. So these are the packets, or the quantized value. The quantum are the packets. This is your spectrum. These are your quantized packets. Okay. And then particles of light. The second truth, light can sometimes behave as a particle. This was initially met with harsh criticism as it ran contrary to the 200 years of experiments showing that light behaves as a wave. Mm. So the theory of Isaac Newton that the light is a particle, but the most accepted one is that light, for 200 years, the most accepted theory is that the light is in a form of wave, much like ripples on the surface of a calm lake. Mm. So just like imagine if this is your lake, you drop something here, like a stone, it will create a ripple. So that ripple is a representation of the wavelength of the wave of the light. Light behaves similarly in that it bounces off walls and bends around corners, and that the crests and troughs of the wave can add up to up or cancel out. So with that, we can try to imagine that why would they think that a light is a wave. Is let's say for example this is a plane surface and this is your wall, and then light goes from here, it will bounce, so that is the main concept why they call that light is in a wave form. And an added wave crest results in brighter light, while waves that cancel out produce darkness. A light source can be thought of as a ball on a stick, being rhythmically dipped in the center of a lake, and the color emitted corresponds to the distance between the crests, which is determined by the speed of the ball's rhythm. Constantly dip. So if this is your ball, you are constantly push and pull it from the water, that it will create a ripple. And the color emitted corresponds to the distance between the crests, which is determined by the speed of the ball's rhythm. So the higher the speed, brighter it does, and the slower the speed, the darker the color is. So waves of matter, that is the third or the last truth of the quantum physics theory. Waves of matter. Matter can also behave as a wave. This run counter to the roughly 30 years of experiments showing that matter such as electrons exist as particles. So in my previous years in education, like in elementary, introduced that particles are matters are like this, produced of particles. That solids has more dense particles, while liquid has lower density in particles, and gas has this like okay, so this is solid, this is liquid, this is gas. So composed of particles. But on the waves of matter, matter can also behave as wave. This run counter to the roughly 30 years of experiments showing that matter, such as electrons, exist as particles. So in a quantum physics, in the development of contemporary physics, from particles, it is now believed that matters, not just particles, but also can act as waves. That's what the previous physicist Albert Einstein proposed, that light is composed of particles but behaves like waves. So these are the particles of light, but it moves in a wave form. Thus the other matters also behave like that. So probability is uncertainty. So what we are trying to uncover in the physics or in the quantum physics is that we try to compute the probability distribution of the particle and a wave. So the higher the wave amplitude is, the higher probability it is, while the lower the wave distribution is, the lower the probability that the particle exists in that certain point of the wave. So then the universe is random. Yes, well, we cannot always predict the real position of that particles. So that is the boundary between how can we compute the quantum world compared to how can we compute the atomic world. Where we see the atoms, we can compute how many atoms, but within that atoms, the subatomic particles, where the wave function exists, the quantum world, we have that probabilities and uncertainty. We could not really determine the exact position. So another example is probability. So this is where the high probability is high. These lights are high in probability, and these darker ones are the lowest on probability. So the Heisenberg uncertainty principle, it is a definite position, a very uncertain momentum. If we can expect the definite position, we are now uncertain with the momentum. But if we are uncertain with the position, and we can always uncertain with the momentum. So very uncertain position and has a definite momentum. So these are the probabilities and uncertainty of the quantum physics and computing the quantum world, the wave function. So the other particles beside photons become waves. So French theoretical physicist Louis de Broglie on 1892 to 1987 furthered such research on the wave nature of particles by proving that there are particles, electrons, protons, and neutrons besides photons that have the properties of a wave. And so according to de Broglie, all particles traveling at speeds near that of light adopt the properties and wavelength of a wave, in addition to the properties and momentum of a particle. So we also derive the relationship wavelength multiplied by the momentum equals the Planck's constant. So from another perspective, one could say that the essence of the dual nature of light as both a particle and wave could already be found in Planck's constant. So the evolution of this idea is contributing to diverse scientific and technological advances, including the development of electron microscopes. So as for the summary of the quantum theory, the quantum physics is a science that describes the wave functions, but when we measure it, we see particles, which result to the particle-wave duality theory. So a theory that matters in the universe are made up of qubit or subatomic particles that behaves like that of a wave, making it harder to predict its probability, leading to the phenomena of superposition, entanglement, quantum tunneling, Heisenberg's uncertainty principle, and then the energy quantization. Let's talk about the superposition. The superposition is already indicated in this example from the video. So you cannot calculate the probability or the specific position of the particle in a wave function. So that's the superposition and the phenomena. And then the entanglement. So the theory of entanglement, so we are going to illustrate it again. So we have this wave here, and then we have some wave here, and that waves are connected whatever the distance. So if these waves are connected even in a million light years, in distance, whatever the value of this whatever the value of this wave, so for example the value of this wave is 1, we can always declare or confirm that the value of this other wave function is 1 without having to measure this one. So no measurement will be done here in this wave because we already measure this wave here, and that we confirm that the value of this wave is 1. Therefore we can already tell, or we can already declare that the value of this wave is also 1 because of this quantum entanglement. So the quantum entanglement. Okay. So with this theory of quantum entanglement, some other wild speculations that because of this quantum entanglement in the quantum world, or in the physics, we could communicate other humans or other species from other galaxies or other planets. So with the concept of quantum entanglement, some others speculate that we can now build a super telephone or a smartphone that could reach farther distance in a couple of seconds. We can we can even travel from, let's say, from Earth to somehow like in Mars or in different universe, I know, in different galaxies, using the faster than light travel, or the FTL, faster than light travel, the FTL concept, because of this quantum entanglement. So that's how wild this quantum entanglement is, according to the science community. So maybe if we can harness this quantum entanglement, we can do that. We can have that FTL drives, or faster than light. So it's a wild theory. It's a wild ambition of the humans to travel faster than light from one place to another place. So but maybe somehow, at some point in time, maybe we will not live long enough to witness that come to reality, but maybe with the development of the contemporary physics, that is, as it continues to grow in an unprecedented what do we call this, unprecedented development stages as we go through with technology. So maybe somehow at some point in time. So another thing is the quantum tunneling. So this quantum tunneling, is this is just my own speculations about quantum tunneling. So it does not really had a bigger explanation or a better explanation in the field of science. But for me, the quantum tunneling in the quantum world, we can transfer an object from one place to another place, or we can have this word teleportations, maybe. So we can teleport object from one place to another place with nothing changes. Like a human or I from here in Pagadan City could be transferred to Jeremy Sudapitan using the quantum tunneling. It's just my wild imagination about the quantum physics. No, it does not uh, back with it was not backed with a scientific research, but maybe perhaps somehow, because most of the movies, the wild movies we've seen so far, are coming to reality. So maybe that one. So the stupidest or the craziest ideas becomes reality in the span of in the future. So maybe somehow someone would develop that kind of technology. Hmm? We can even maybe travel forward in time or backward in time. So yeah. In generalization, quantum physics is about science that describes the wave functions, but when you measure it, we see particles, which result to the particle wave duality theory. So let's talk about this. I have seen a comment from the video I played a while ago. So that video has a comment that it says something like this. Imagine this, in your peripheral vision, you've seen someone dances and dances and dances and dances, but when you observe it, that someone is as steady as statue. So it is not moving, it's not dancing at all. It has a still position. But when you're not observing it, when you're not looking at it, it creates somehow like a wave. It's dancing. Okay. So in quantum physics, that that is something like this is your wave in a quantum world, and that wave is represented in our world as particles, but that particles has no value at all. You don't know the exact value of that particle. And then if you're not observing it, when you're not observing it, this particle has no value at all. It has a question mark value. It could be 1, it could be 0. So either of the two. But when you observe that particle, it will give you a definite value, like 1 or 0. Now in information and communications technology, we applied that concept in in quantum computing. The qubits. So transistors and a computer are composed of the processing or the processor of a computer composed of bits, but we can divide that into qubits, and that qubits will act like this quantum wave function, where when you are not observing it, that qubit has no value, but when you observe it, it will give you a definite value of 1 or 0. So with that in mind, with that concept, our supercomputers will produce a massive advancement in computing, in the world of computing, because that qubits or that particles now inside as qubits inside the central processing unit of the computer, transistors. It will hold, or it can process multiple values at simultaneously in a span of maybe lower than nanosecond. So it will produce values and results because of that concept of quantum computing, quantum world, the quantum physics, quantum mechanics. So again, the basic concept of quantum physics is that all objects, all matters, okay, so all matters are composed of particles, and these particles act like waves, and we try to compute this wave for the probabilities of its position and quantity of that particles that produces matter. Okay, so that's all for the development in quantum mechanics or quantum physics, starting from the Big Bang, going to the alternative theory of the Big Bang, and then to the theories of quantum physics, quantum mechanics, and its difference to the classical physics. Okay, so that's all for the topics of the development and quantum physics. Thank you for watching this video, and if you have questions, you can comment down below. If you have additional knowledge on or discussions on the topic, you might as well comment down below to give additional information to the viewers. Thank you so much.